from last time. So it was these 6 problems. So if you have those with you, I would say to take it out. If you have questions on anything, we can do a couple of these here in class together, or talk about what's going on, or whatever you might need. But this, again, is your main chance to kind of get some feedback before the homework checks happen. So if there's something you're not sure about, or something you want to just double check, or you want to see done, or any of that kind of thing, now is the opportunity to have that happen. Bianca?
Can we just do
Sure, we can do 3. So again, I'm going to talk through verbally the questions that I'm kind of asking, or the things that I'm referencing is that flow chart for the factoring that we made last class period. Just so everybody's on the same page, what the heck is he talking about? I'm talking about the questions from that flow chart, right? So the first thing we'll check for is a greatest common factor. If we look here, clearly there's no greatest common factor, because 64, the only factors are divisible by 2. And for 125, the only factors are divisible by 5. So obviously 2 and 5 don't divide each other. And there's x's in one, but no x's in the other. So there's no greatest common factor here. So it has 2 terms. So we go down the 2-term branch. And the first thing we check for is a difference of 2 squares. Clearly that's not what this is, because the exponent on the variable is odd. And it's also an addition problem. So on 2 counts, you can tell pretty quickly it's not a difference of 2 squares. Then we check to see if it's a difference or sum of 2 cubes. Well, we have an x to the third, so that's usually a pretty decent indication that this could be a sum or difference of 2 cubes. So that's what we're going to try to do here to see if that'll work. So let's see if we can write this as something cubed plus something cubed. So obviously x cubed is just x to the third. So I know that there's going to be an x in that first one. And then I have to look at 64. Okay? Well, 4 times 4 is 16. And 16 times 4 is 64. So I know 4 to the third is 64. Similarly, 125, 5 times 5 is 25. And 25 times 5 is 125. So 5 to the third is 125. So this is a sum of 2 cubes. So I will factor this using our sum of 2 cubes factoring pattern. So I'll write that down here so that it'll be easy to see what I'm doing, or what I'm referring to when I do this factoring. So in our case, our a is like 4x and our b is like 5. So I'm just going to fill in this part now. So a plus b would be 4x plus 5. And then a squared is 4x squared minus a times b. 4x times 5 is 20x. And then plus b squared, well, 5 squared is 25. And then I didn't square the 4x here immediately because I wanted to make sure that we're being clear that 4x squared is 4x times 4x, which would be 16x squared. I just made an extra step there so it would be a little bit easier to follow where the 16 was coming from. And now I need to check these pieces to see if they're factorable. So 4x plus 5 is linear, right? It's a degree 1 term, so I know that one doesn't factor anymore. Because it can't be a difference of 2 squares, it can't be a sum or difference of 2 cubes because its degree is too small. And then the trinomial part came from the sum or difference of 2 cubes, and we said the trinomial part from the sum or difference of 2 cubes will never be factorable for us, providing we're doing things in the correct order. So this is as good as we can do. Does that feel okay, Bianca? Yeah, you're welcome. So again, like familiarizing yourself with some of those perfect cubes is often going to be helpful. You know, like 1, 8, 27, 64, 125, 216. what's 9, what's 7? I forget 7, like 249 or something maybe, or 243. Yeah, maybe 243. 8 is 256, I remember that. 9 is 343. So maybe 7 was, I don't know. Anyways, that's beside the point. But that can be helpful. Let's see, Lily? 2? Sure. So I'll use a different color here. Okay, so again, starting the same way, first thing we do is check for a greatest common factor. Clearly there's not one because the other term is just a 1, right? So there's no common factor going to work there. This has 2 terms, so going down the 2-term branch, the first thing I look for is a difference of 2 squares. Definitely not that because the exponent on the variable is odd. Can't have a perfect or a difference of 2 squares with an odd exponent there. So then we'll look at the sum or difference of 2 cubes because I see an x that's got an exponent that's divisible by 3. That's a good chance that this will work. So let's try to do that. So I'm going to try to write this as something cubed minus something cubed. Well, clearly in the first piece, I know there has to be an x in there because I have an x cubed in my problem. And then 8, I recognize as 2 times 2 times 2. So I know 2x to the third is the same thing as 8x cubed. And then 1, well, I know 1 is just 1 times 1 times 1, right? So 1 cubed will also work. So using the difference of 2 cubes factoring pattern that I'll write down here for us real quick. Here I see that my a is 2x and my b is 1. So this can be 2x minus 1 and then 2x squared plus 2x times 1 plus 1 squared, which is just 1. And then if I do the 2x squared, 2x, and again, that's as good as we can. The first piece is linear, and the second piece was the trinomial that comes from a sum or difference of 2 cubes. And we know those aren't factorable. Does that help, Lily? Yeah. You're welcome. Others from this. Happy to do more if there is any more. If there's not, that's okay too. Okie dokie. So today, we're going to kind of continue talking about factoring polynomials. So we're not going to add any more content to this idea today. I'm just going to do some more practice on factoring these polynomials now that you had a chance to practice a little bit on your own and have maybe a little bit more familiar with that factoring tree. We're going to do some more factoring examples. We'll do, I don't know, 3 or 4 of these just to get a little bit extra practice here. And we'll do some more of that in the homework tonight. And then we'll take one little baby step forward and when we talk about solving by factoring. And that'll be it for today. So it'll be not much moving forward. We're just kind of mostly staying in place here as we get a little bit more comfortable with these factoring techniques. Because again, this is not easy, right? It's the first time you're doing a lot of this. It's going to take a little bit of time to get comfortable doing this, although the fundamental skills we should feel good about. Using them in combination, those can be kind of tricky. So I want to make sure that we take a little bit of time here for everybody to, do some work and get things sorted out for themselves. Because once you've got it, it's not too bad, but getting it can be, can take a little bit of time, and that's okay. So again, we're just going to do some practice problems here. So the typical instruction when we ask you to factor a polynomial is to factor completely. By that, we just mean we want to do all the factoring that's possible, right? So it's just a clarity thing. It doesn't really mean anything new per se. So here's, we'll do, I don't know, like 3 or 4 again, examples, and then we'll move on and talk about solving. When I do these examples, I'm going to write some additional notes, just referring to like where I'm at in that factoring diagram. That's not something that you guys necessarily need to do when you're doing your homework or doing a test or a quiz. If it helps you, certainly by all means, you're welcome to do that. Mostly I'm doing this so that when you refer back to your notes, it's a little bit more clear like what I was doing or what I was thinking about when I moved from one step to the next. Just kind of reminding you that at all times I'm basically just using that factoring tree to figure out what to do next. Okay? So if I look at my factoring tree, the first thing is look for a greatest common factor. So in this problem, is there a greatest common factor? What do you guys think? Okay, so 4 we can take out of the coefficient, right? Because 4 divides 4, it divides 16, it divides 180, but there's a little bit more. X also, right? If we look at the variables, the smallest exponent on our variable is 1. They all have at least an x. So I can take a 4x out, and that leaves me with x to the 4th minus 4x squared minus 45. Is everybody okay with what I did to get to there? So just for the record, once we take that greatest common factor out, we're basically going to ignore it from here on. Like it doesn't have any more impact in the problem. It's just going to sit there out front. We need to take it with us every time we go on a next step to next step to next step. But we're done worrying about the 4x. That part is basically finished. What we're going to be continuing to work on now is this stuff that's left over. So every question that we ask from here on is about this leftover piece. So after we take out the greatest common factor, the next thing we look for, or what we next ask, is what the number of terms is. 3 terms. Good. Right? Because we have 3 things that are either added or subtracted together. Okay. If I look down that 3-term branch in the quadratic form. Yes. So again, to look at the quadratic form, what we do is we look at the biggest exponent on our variable, should be twice the smallest exponent on our variable, and then the last piece has to be a constant, which is what we have here. So we can continue down, since we are in the quadratic form. After that, we want to know is what the leading coefficient is. Is the leading coefficient equal to 1 or not? In this case, it is. And now all of that line of reasoning then tells us that we can do the shortcut factoring. So I just need to find negative 45, add to give me negative 4. Does anybody recognize the 2 numbers that do that? Negative 9 and positive 5 is correct. So So those complete that. And since this is the short numbers, we'll go straight to my factored form. Something plus 5. I want to point out, though, that this something is not going to be an x. It should match in our problem there. Sorry, hold on. My computer is going slow and I want to stop the Zoom call because nobody's on it. Okay, so in this case, 9 will have x squared minus 9. I swear I picked that. And x squared plus 5. Okay. And again, that's something that's easy to forget to do, but it's really important that you remember to do that. That the exponent on the smaller of the variable pieces should be the exponent in your factors, right? Okay. So we've completed the 3-term branch. So now what we have to do is we have to take these 2 factors and take them each through the 2-term branch. So we'll start with the x squared minus 9. Going through the 2-term branch, the first thing we do is we look to see, is it a difference of 2 squares? Yes. So we should be able to factor that. And since this is like strictly quadratic, that should be an easy thing to factor, right? For the x squared plus 5, again, we start with the same question. Is it a difference of 2 squares? No. And really for 2 reasons. One, it's a sum, right? And the second, 5 isn't a perfect square. So then we ask, is it a sum of 2 cubes or a difference of 2 cubes? Clearly not, right? Because the exponent is too small. It has to be at least 3. In fact, it has to be a multiple of 3, minimally, for that to work. So again, no there. So we can't do anything else with the x squared plus 5. So that, oops. Look at what we forgot to do, though. What did we forget about? Yeah, the 4x. That should have come down with us. Oops-a-daisy. Yes?
What is the limit you said on the x?
Well, I wrote SOTC and DOTC with a question mark after for sum of 2 cubes and difference of 2 cubes, just an acronym. That's what you wanted, right?
Mm-hmm.
Okay. Yeah, you're welcome. Again, I recognize that my penmanship is not spectacular, so if, again, you're having trouble reading anything, please don't hesitate to ask. Lily.
Okay, so I understand that x minus 3 is x plus 2, but why did you put x squared plus 5?
So that's because this piece here, we couldn't factor it anymore, so it just comes along with it, right? So the x squared minus 9 turned into these 2 pieces. Maybe I should have used a different color than yellow. But the x squared plus 5, we couldn't do anything to, so that just had to stay the way it was. Does that make sense?
Yeah.
Okay. So again, we're just going like from one set, like one factored form to the next factored form. And some parts we can change, but the parts we can't, we still need to take with us to the next step, right? So that's all that's going on there. That feels more clear? Okay. All right, you guys ready to do another? Okay. Is this feeling a little bit, I don't know about easier, but at least clearer? after spending a day on homework working on this stuff a little bit. I know it's going to take a little bit of time to get really good and comfortable with things, but hopefully, doing some more practice here together. And I hope that am I going slowly enough? I'm trying to make sure that I'm not just burning through stuff. I have a tendency to get rolling sometimes. If that's happening, you can please let me know that, like, hey, just can you take like half a beat and slow down a little bit, and I'll try to do that. But I know it's not easy, right? Maybe the individual little tiny pieces are not difficult, but managing all of the interplay between these different little tasks can be a little bit daunting here, especially in the beginning. So if this is hard, don't feel bad. It is one of the harder topics that we do. And that's okay, because it's got a lot of ideas going on here. All right, so let's try the next one. So the next one, we have 2x to the 7th plus 6x to the 5th minus 16x to the 4th minus 48x squared. So we're starting over with our factoring diagram here. The first thing we look for is a greatest common factor. Do we see one in this case? 2x squared, very good. So we can see that each of the coefficients, 2, 6, 16, and 48, are all divisible by 2. And if we look at each term has a variable. The smallest of those degrees is x squared. So when we take that out, I have x to the 5th plus 3x cubed minus 8x squared minus 24. And now as we continue, we're only really worried about this piece, right? The 2x squared out front we ignore. We just have to kind of hang on to it, but we're done. It's done telling us anything, or we're done using it to do anything. So after the greatest common factor, we have to look at the number of terms. How many terms do we have in this case? 4 terms. So if we go down the 4-term branch, the first thing it says is to check if we can factor by grouping. Yes, Bianca?
I'm not sure. Okay, this is a weird question, but it's x to the 5th. So is that coming from the 2x7? Why wouldn't it be 6?
Well, because we took an x squared out. We took 2 x's.
Oh, okay.
Right, so each of the exponents went down by 2.
Okay.
Yeah, no problem. Not a weird question at all. Okay, so we decided we had 4 terms. So on the 4-term branch, we have to check to see if it's factorable by grouping. So the way we do that is we group the first 2 terms together, and then we put a plus sign, and then we group the second 2 terms together, and then we look for greatest common factors. Notice here, though, that importantly, the problem was minus 8x squared. And really, I wrote this as like plus a negative, right? Always have to have a plus sign there in between our 2 groups at that grouping step. So if there is subtraction, it's an easy workaround because we just write it as plus a negative. Okay. So the x to the 5th plus 3x cubed, we look for a greatest common factor there, which would be x to the 3rd, or x cubed. Yep. That leaves us with x squared plus 3. And then we'll look at the second group, a negative 8x squared minus 24. The greatest common factor there is negative 8. And we factor that out. That leaves us with x squared plus 3. And now to determine whether this is factorable by grouping or not, we check these 2 pieces and make sure that they're identical, which they are. So this is factorable by grouping. So we can kind of continue this process. If those two pieces weren't identical, then you could conclude that this just wasn't factorable anymore. And this step here would be as good as you could do, right? Because the grouping didn't work. So you go back to the next factored thing that you could do. Okay. So since this does work, we can continue this process. Since each of these two contain the x squared plus 3, we can factor that out. And that leaves us with an x cubed minus 8. Now we've completed the 4-term branch. So we have to take each of those two factors that we just created and check them through on the 2-term branch. So x squared plus 3, we'll do that one first. First thing we check, is it a difference of 2 squares? No. And we can tell that because it's an addition problem or because the 3 isn't a perfect square. Either one of those is justification. Then we have to look at, is it a sum of 2 cubes or a difference of 2 cubes? Again, no, because the exponent isn't a multiple of 3. So there's nothing more we can do with that piece, so that just stayed the same. Now we'll do the same set of questions on the x cubed minus 8. Is that a difference of 2 squares? No. Is it a sum of 2 cubes or difference of 2 cubes? Well, certainly looks like it might be, right? Since it has an x to the third. So let's try to do that. So clearly we can write x cubed as x to the third. And then we need to rewrite 8 as something to the third. Well, I know 2 times 2 is 4, and 4 times 2 is 8. So 2 to the third has to be the same thing as 8. So this is a difference of 2 cubes. So the factoring pattern here I'm going to write down on the side again for us so you can see what I'm using to do this. In this case, my a is x and my b is 2. So I'm going to have x minus 2, that's a minus b. And then I'm going to have x squared, that's a squared, plus 2x, that's a times b, plus 4, which is b squared. And then those other two pieces are just going to come down. Again, we couldn't do anything with them, so they're just kind of keep hanging on. After we've decided there's no more factoring we can do with that piece, it just continues to follow. We don't do anything with it, but it needs to be in the final answer. So now we just need to check the results. The x minus 2, we know that can't be factored anymore because it's linear. And the trinomial piece was the trinomial from a difference or sum of 2 cubes. So we know that piece can't factor anymore. So we know we've done all the factoring. And we are finished, and that is our final answer. So far, so good? Is it feeling at least a little bit more comfortable using the flow chart and knowing the questions to ask and what we really mean by that question, how these things kind of all fit together? Again, I know it's a lot, and again, we're not really moving forward much at all today, so don't, I recognize that I'm asking from a lot from you guys, so we're taking it slow in terms of, we did a lot in one day and now we're slowing down a little bit so we can kind of catch up or get more comfortable feeling, or however you want to put it. We'll do one more example here together. And actually, let's think about it this way. I'm going to write this one down. I'm going to give you guys, 5 or 6 minutes here to work on this one, and then we'll go through it as a group so you guys can try to do one at least starting it without my help. And again, it doesn't matter how far you get. If you finish it or don't finish or get it right or wrong or any of that kind of thing, it's just an opportunity to, we've done a lot of this now together. Let's try to do a little bit on your own. If you need to go back and look at the other examples or go back and look at the flow chart or any of those sorts of things, look anything up you would like. That's perfectly fine. It's just often helpful to, look at stuff on your own before we get before we do it together, or before you see me do it, right? It gives you a chance to try stuff. And I'm going to stop talking now and let you concentrate, as I tend to babble. Boy, that's embarrassing. All right, should we go through this one here? Are we ready? I hope so. So the first thing you should have checked is a greatest common factor. You would have found that there was none. We look then to the number of terms, which is 3. It is in the quadratic form. The leading coefficient is 1, so we can do our shortcut factoring by finding the two things that multiply to give us negative 27 and add to give us 26. Shouldn't have hopefully been too hard to see. That would have been positive 27 and negative 1. So we can write x cubed plus 27 times x cubed minus 1. When I go through the first one, I'll check to see if it's a difference of 2 squares, which it's clearly not. And then we'll look at sum of 2 cubes or difference of 2 cubes, and that it is. Right? We can write this as x cubed plus 3 cubed. Similarly, over here, it's not a difference of 2 squares, but it is a sum or difference of 2 cubes. We could write this one as x cubed minus 1 cubed. So when we factor this, we're going to get x plus 3, that's a plus b, times x squared, which is a squared, minus ab, which is 3 times x, plus b squared, which is 9. And then for our other piece, we're going to have a minus b, so x minus 1, times a squared, plus a times b, which is just x, plus b squared, which is 1 squared, which is just 1. And this is as good as we can do, because the binomial terms are linear, and the trinomial terms are the results of a sum or difference of 2 cubes factor. So that's as good as we could have done. Is everybody okay on that one? Okay. Hopefully you got at least close on that, right? I would have hoped that we could have at least gotten to through the quadratic or the 3-term factoring piece. That hopefully should have been relatively easy there. Okay. So I want to talk a little bit today. We'll take one little baby step forward and talk about solving polynomials by factoring. And the tool that we'll use to do this is that zero product property that we talked about in chapter 4. And the zero product property says that if we have two things multiplied together that give us 0, one of those two things has to be 0. So in chapter 4, we use this to solve things like x squared plus 9x plus 18 by first factoring and then setting each of those factors equal to 0, and then solving these factors separately. Right? You guys remember doing that last semester, I hope? So this is the same idea that we're going to do now for polynomials. The hard part about this is going to be the factoring part. But once we have the polynomial factored, it's really not going to be appreciably different than a chapter 4 question. Okay with that plan? So what I'm going to do, for the in the interest of kind of saving time, is I'm going to go back and do our solving examples using the same polynomials that we already factored in the previous 3 examples, so that we can just borrow the factoring work from our previous examples and not have to do the factoring all over again. So we can just worry about the solving part in those examples. Is that okay with you guys? So I'm going to change my color and I'm going to go back to where we did the factoring examples, and just on the other side of it, I'm going to make a solving problem and do the solving part. Okay with that? So I'm going to go back to each one of these 3. So we're just going to turn this into a solving problem. So because it's a solving problem, it needs to have an equal sign in it. Notice that the start of this question looks a little bit different than the factoring only question that doesn't have an equal sign on it, right? So we'll use the work that we did in the previous problem to factor this. Everybody okay with how I shortcutted through that? Now normally the hard part is the factoring part, but because we're just worried about practicing the solving piece to this, we're still getting good at the factoring part. So I don't want to turn this example into something that was took a million years, where by the time we got to the solving part, you guys were already bored because the factoring part took so long. So what we can do now is we can set each of these pieces then equal to 0. And solve each one of them separately. So 4x is equal to 0, so I can divide both sides by 4. I get that x is equal to 0. X minus 3 is equal to 0. I can add 3 to both sides to get x equals 3. X plus 3 is 0. I'll subtract 3 from both sides to get x equals negative 3. Now x squared plus 5 is equal to 0 is quadratic, right? So remember, there are 3 ways that we had to solve a quadratic. You could solve it by factoring. That'll never be an option for one of these problems, because if we could have factored that more, we would have when we factored the polynomial, right? So the quadratics that we're left with in these polynomial factoring problems will never be factorable, right? Or else we would have factored it more. So that leaves us with either solving directly or using the quadratic formula. In this case, because it has only x squareds in it, either of those options would be appropriate. I'm going to solve this directly because I think that's a little bit easier than using the quadratic formula, but not really appreciably easier. So I'll just subtract 5 from both sides. I'll square root both sides. Because I square root both sides, that creates a plus or minus. Because I'm square rooting a negative, that creates the I. And then the square root of 5 can't be simplified, so that's as good as I can do. And I'm done. So again, it's just basically a little add-on to the factoring problems that we had just done, right? Okay, let's look at the next one here. So again, I'm just taking that previous problem. I'm going to steal its factoring work. So again, we just stole the factoring work to get to this point.
Can you scroll just like a little?
And I can use that to set each piece equal to 0. So the first piece, 2x squared, is equal to 0. I can just solve this directly because, well, it's just a monomial, right? And I don't have to worry about the plus or minus because the square root of 0 is 0. So plus 0 and minus 0 is just 0 is 0, right? Whether it's positive or negative doesn't matter. The next piece I'm going to solve just like I did the x squared plus 5. I can solve this directly. You can use the quadratic formula on those if you'd like. I don't think it's appreciably any harder. But it's basically kind of the same problem as that previous one was. So the plus or minus comes from me square rooting both sides, and the I came from the fact I was square rooting a negative. And then x minus 2, we can just add 2 to both sides and be done there. Now x squared plus 2x plus 4, I cannot solve directly because it has both x's and x squareds. For this one, I have to use the quadratic formula, which again is x equals b, negative b plus or minus b squared minus 4ac all over 2a, if you didn't remember. Okay, so we have 4 minus 16 is negative 12. And because we're square rooting a negative, we're going to get an I. And the square root of 12, I can think of as the square root of 4 times the square root of 3. Everybody's okay with that because 12 is 4 times 3. Now the square root of 4 is just 2. And the square root of 3 we can't do anything else with, so I can do that and write it as 2i square root 3. And then if I think about this as two separate fractions that have that common denominator of 2, the first fraction reduces to negative 1, and the second fraction reduces to I square root 3. And that's our best answer. Although I still would, on a test or quiz for this class, I would accept negative 2 plus or minus I square root 12 over 2. As long as you got the I on it, the I on there, I probably would have been pretty happy with that, and you gave me an equivalent answer. But if you're taking an SAT or ACT or something like that, they're definitely, the one that I boxed at the end would be the one in the multiple choice. So far, so good? Okay, the worst case scenario is when we have to do like that full quadratic formula on these. And our last one is this one. So again, we factor this. I'm going to steal all that work. And just like we've done for each of these examples, once we have it factored, we just set the factors equal to 0. And then we can solve them each independently. So the x plus 3 equals 0. That's easy to deal with. Subtract 3 from both sides. The x minus 1 equal to 0. That's easy to deal with. We just add 1 to both sides. The other two pieces we have to use the quadratic formula on. So x equals negative of negative 3 plus or minus square root negative 3 squared minus 4 times 1 times 9 all over 2 times 1. Negative 3 squared is 9. 4 times 1 times 9 is 36. 9 minus 36 is negative 27. So we have 3 plus or minus I square root 27. And I recognize that 27 is 9 times 3. So square root of 27 is the square root of 9 times the square root of 3. The square root of 9 turns into 3. So that's our best answer there. And then for this other one, x equals negative 1 plus or minus 1 squared minus 4 times 1 times 1 all over 2 times 1. Negative 1 plus or minus square root negative 3 over 2. And we just need to get the I in there from the negative under the square root. And that's as good as we can do with that one. So again, the solving the polynomial, not really a difficult problem. The worst case scenario, it turns into solving a quadratic like we did last semester in chapter 4. Now there could be multiples of those inside of one polynomial. But the whole idea is you take something really complicated and you break it up into these smaller pieces that are each relatively easy to deal with. So instead of having one really difficult problem, you break it into like lots of little tiny, smaller, easier problems. And that's the general idea with polynomials. Does that feel okay? All right. So again, the only thing that we did new today was this idea of solving, which wasn't really much of a step forward. We just used the concept from first semester, applied to second semester, and did some examples. So it wasn't really even much of a step forward. It's like a little tiny half baby step. So I'm gonna stop here because we've done a lot, right? You guys need a chance to practice and process. So the assignment for this I've posted here on the content library on OneNote. So this is the homework 3. The first 5 problems I ask you to factor completely. The second 5 problems I ask you to solve by factoring. So on those second 5, you're going to have to factor and then take those answers and solve them, or take those factors and solve them to get your answers. So you won't be able to shortcut around doing the factoring because you won't have done the factoring yet for those problems. But so do the best you can with that. When we meet next time, we'll take questions and the whole shebang. Okay? Lily.
So one of the answers, I started doing these answers, one of the answers, I got x times x squared plus 1x plus 1. Would the answers, would one of them cancel out that? Or?
Okay. What are we referring to now, real quick?
I started number 5, and I got x times, or I got like one of my answers. I wondered if I could distribute it, or if I do it.
Maybe just come up and show me what you have, and it'd be a lot easier if I can physically look at what you're describing, because I'm not sure I have a good picture of what you have written down on your paper from the words that you're using. But come on up here, and I'll be happy to look at what you have and give you individual feedback on that kind of thing. But we're done here for today, guys, so you can